share in WhatsApp and Blackboard, inshallah. All right, so inshallah, you and your all of your families are fine during these challenging war conditions, and everyone are okay and healthy. So after a long time, we return to our classes, and now I want to start after power flow analysis section. We would like to begin the fault analysis section. So let me add a new student in the class. All right. Uh, so this lectures we are focusing on one of the most important analytical tools in power system. It calls symmetrical components and their applications in analyzing the unbalanced faults. And because in power system one, you're already familiar with balance fault systems, so that's why here, as I told you at the beginning of this module, we want to talk here about the unbalanced fault. So first of all, we will talk about a little what is fault and what is the impact of the fault in the power system and so on, and then we can start to see how we can analyze the system. In real-world power systems, faults such as single line to ground or line to line and double line to ground faults will create asymmetrical conditions that cannot be easily analyzed by using of standard balance system techniques. And symmetrical components can provide a powerful method to simplify these complex conditions by transforming unbalanced three-phase systems into three separate balance sequence networks, including positive, negative, and zero sequences. Uh, Let me add. All right. Um, Throughout this lecture, we will explore how this transformation works and why it is essential for fault analysis and how it enables you to accurately calculate fault currents and system behavior under abnormal conditions. And understanding all of these concepts are very fundamental for designing protection systems and ensuring that the stability and reliability of the electrical power networks are guaranteed. All right. In this slide, I want to introduce the concept of fault in electrical power system, which typically occur due to the failure of insulation around conductors or equipment. So when insulations breaks down, it will create a short circuit and it can provide an unintended low resistance path for current to flow. And as a result, a very large fault current can be created, and we will have exceeding normal operation levels currents, and uh, such kind of high currents are very dangerous and must be interrupted quickly to prevent serious consequences and um, make a negative impact on our devices. So, if not clear at that time, fault currents can damage or destroy equipment, and can make some unsafety risk and lead to instability in the entire power network. So therefore, understanding faults and their behaviors are very essential for designing effective protection systems that ensure both safety and reliability of the system. All right. In this slide, I want to explain the various cause of faults in electrical power networks and highlighting both natural and human-related factors. One of the most common cause is lighting, so which can introduce extremely high voltages into the systems and damage insulations. And faults may also occur due to physical contact between the conductors, often resulting from environmental conditions or mechanical issues. And external elements such as tree branches or animals like squirrels, snakes, and large birds can create um, um, unwanted conditions between the conductors, and it will make fault for the systems. Additionally, conductor movement caused by wind or excessive sagging due to high current levels also can lead some faults in the systems. And material related issues also play significant roles to make a fault for us, and defects in insulating materials, aging of the solid insulations, or contamination of insulating oil, and environmental pollution also can gradually weaken system reliability and make fault for us. Uh, and In addition, physical damage to insulators, whether from natural causes or human activities such as construction work or other unwanted activities, can further increase the likelihood of faults. So the probability of the faults can be increased. Even a small creatures like rats or ants can contribute to insulation damage. So, moreover, pollutions also uh, pollutions around the installations, especially in coastal or maritime areas, can reduce their effectiveness and lead to flashovers and making some big issues in the power system. And understanding all of these reasons um, and faults are very essential for preventing faults and improving the resilience of power systems. All right, this slide focusing on lighting as a major cause of faults in power system. Lighting creates a highly ionized path in the air, and which allows electrical current to travel between the clouds and the ground, or between different parts of the systems. In US, there are approximately 30 million lightning strikes each year, depending on the state in US, demonstrating how frequent and impactful this phenomena can be happen. And let me, all right. And a single lighting stroke can carry around 25,000 amp of current, so you can imagine how it is. And with an extremely fast rise time of about 10 microsecond, and a total duration of roughly 200 microsecond. In many cases, a lighting flash consists of multiple strokes occurring in rapid succession, and which makes it appear as a fleeting event and can last up to 1 second in total operation. And during this process, the ionized air acts as a conductive path and allowing the fault current to continue following the power system, so it will make more dangerous even. So this makes lighting particularly dangerous for power system, and as you know, it can easily lead to installations breakdowns or equipment damage, and also system disturbances if proper protection measures are not provided for the systems. All right. Faults in power systems are often caused by external and unpredictable factors, with lighting being one of the most significant. As shown in this slide, lighting strikes can directly hit transmission lines or nearby structures, creating extremely high voltage surge that exceed the insulation strengths of the systems, as you can see in this slide. These transient over voltages can lead to flashover, insulation breakdown, and ultimately short circuit or line outages. Even indirect strikes can induce electromagnetic disturbances that propagate through the network, affecting equipment performance and reducing the reliability of the systems. All right. In this slide, highlighted another critical cause of faults in the power system: physical damage and environmental impact on infrastructure. As you can see in this figure, external factors such as mechanical stress or weather conditions or accidental contact can damage cables and insulation layers. Sometimes wear and tear combined with environmental impact may lead to insulation degradation, cracks or breaks in conductors. These defects can result in short circuits, ground faults, or even in complex system failures. Therefore, regular inspection, preventive maintenance, and the use of robust materials are essential to ensure system reliability and to minimize unexpected outage. All right, in this slide also emphasize a human-related cause of faults in power system, particularly those resulting from careless or accident. As you can see, activities such as reckless driving can lead to vehicles accidents with utility poles or nearby infrastructures, causing severe damage to transmission and distribution lines. All right. Such incidents may result in short circuit, equipment failure, or even fires or explosions, and maximizing risk to both system reliability and public safety. Even this damage can be happened in outside or even inside the substations. These types of faults are often unpredictable but can be mitigated through better safety regulations or public awareness. For example, adding some sign around the infrastructures and strategic placement or protection of critical infrastructures. Okay, in this slide, we want to highlight one of the major cause of faults in power system. Severe weather conditions, particularly show snow and ice. As we can see in this figure, The accumulation of ice on transmission lines and towers added significant weight and mechanical stress. This can lead to the bending or even collapse of structures, as well as snapping of conductors. In addition, ice buildup can cause also lines to come into contact with each other or nearby infrastructures, creating short circuits. And these weather-related faults are often widespread and difficult to repair quickly, making them a critical concern for power system reliability and also infrastructure design. All right. This slide illustrates another common cause of faults in power system: excessive current. When too much current flows through a transmission line, it will generate excessive heat, causing the conductors to expand and sag. As shown in this figure, the this increased sag can reduce the clearance between the line and nearby objects such as trees, and you can see uh, is um, is increasing the sags. If the conductors comes into contact with vegetarians or gets too close, it can result in short circuit or flashover. Therefore, controlling current levels and maintaining proper line clearance are essential to prevent such faults and ensure safe and reliable operation of the networks. Okay, this slide summarizes the main effects of faults in power systems. Faults can lead to both sustained and momentary interruptions, ranging from long outages to brief disturbances that may only require equipment reset. In more severe cases, faults can cause fires, significant equipment damage, and even pose serious safety risks such as electrocution or any other problems. Additionally, they often result in voltage dips and overall system disturbations. And as indicated on the right, events like short circuits, line disconnections, sudden generator trips, or large load changes can trigger voltage and frequency fluctuations, and it can lead to oscillation in the power systems. If not properly managed, these disturbances can escalate into instability and widespread blackouts, highlighting the importance of fast protection and control mechanism. All right. This slide focuses on one of the most serious consequences of electrical faults: fires. So, faults in power systems can uh, ignite forest fires, which have become a major and a growing concerns in recent years, especially when overhead lines interact with dry trees. In urban environments, faults can also lead to manhole explosions caused by different mechanisms such as gas buildup or electrical arcing in underground cables. So, in addition, electrical faults are also a significant cause of house fires, which result in um, more injuries each year regarding the electrocution. These examples highlight the critical importance of proper system protection, maintenance, and monitoring to prevent fire-related hazards. So we need to identify first the hazard area and then try to minimize any risk in the system. So also I added a YouTube video here to regarding the manhole explosions. All right. In this slide, I want to highlight the severe impact of power system faults in causing forest fires, particularly in the western US. Several major incidents have been linked to the faults on both transmission and distribution lines, and it can lead to widespread um, distraction, losses of life, around 100 fatalities. So, and billions of dollars in damaging of our system. In many cases, inadequate maintenance of electrical infrastructure has been identified as a contributing factor. In, for example, in California, the legal framework of inverse condemnation holds utilities financially responsible for damages caused by their equipment, regardless of fault. And a notable example is Pacific Gas and Electric Company, which faced massive liabilities from the 2017 fires, leading to disruptions. And the company also um, pleaded guilty um, to paid approximately 85 million dollar in fines and in penalty. These events underscore the critical importance of the system reliability, proactive maintenance, and robust protection strategies to prevent such unwanted outcomes. All right, this slide also highlights the 2020 Marlin fire in Washington, devastating wildfire event driven primarily by strong winds that rapidly spread the flames across the area. And the intensity of the wind not only accelerated the fire's movement but also contributed to infrastructure damage, including large branch falling onto a power line, which is believed to have played a role in the ignition. So as a result, the fire caused a significant destruction, with 67 houses lost in a very short period of the time. And despite the scale of the damage and the speed of the wind at which the fire spread, it is north mentioned to here that there was no losses of life, reflecting effective emerging response and evacuations efforts. So this event serves as a powerful example of how extreme weather conditions can amplify wildfire risk and impact communities in our systems. All right, you can see here a video regarding the if we what happened when a fault cannot be clear. So please later on, I cannot show here in the online session. So later you can see this video. And I also faced with some similar event when I was working in the one petrochemical company, very dangerous, and the all of faults should be clear very fast, in the system. All right. This slide explains the consequence of the fault that is not clear promptly in a power system. When a fault persists, it creates a low impedance, and that allows a large current to continue following, which can quickly overheat and damage critical equipment such as cables, transformers, and generators, while also increasing the risk of arcing and fire. If the primary protection systems fails to operate, backup protection mechanisms attempt to isolate the fault by tripping breakers, ensuring that the issue is contained even if it affects a large portion of the networks. However, the continued presence of the fault current can lead to system instability, uh, disrupting the balance of voltage and current and causing voltage dips and frequency deviations. In several cases, this instability can escalate into cascading outages or even widespread blackouts. Ultimately, if the fault remains unresolved, additional parts of the network may be disconnected as a protective measure, isolating larger sections of the grid to safeguard the overall systems. All right. This slide also highlight a real-world incident related to um, sagging transmission line and its serious consequences. The case refers to an explosion at a substation in Dronten, which resulted in approximately 300,000 customers losing power for about an hour. Due to the severity of the incident, significant infrastructures, including cables and other equipment, had to be replaced, and transmission line itself was damaged. And you can see the video here, very interesting. Please have a look later at home. The root causes of the problem are also outlined. Maintenance work was being carried out at the substation, and although grounding was applied for safety, the workers were unaware that the line was still energized. Additionally, the protection system failed to operate correctly, which allowed the fault to escalate into a major outage. This example can emphasizes the critical importance of the proper coordinations, accurate system status awareness, and reliable protection mechanisms in power system operations. So, considering all of those factors, including the um, suitable awareness for workers, grounding the systems, and so on, can minimize the any fault in our power networks. All right. This slide also is illustrating the physical consequences of a sagging transmission line on nearby infrastructure, especially railway tracks. When a transmission line sags exceeded, it can come into unintended contact with surrounding objects, and such as rail tracks. In this case, the this figure showing that the clear damage to the rail likely caused by electrical arcing or fault current passing through the metal structures. You can see here uh, there is some arc here, and such incidents can lead not only to power system failures but also to significant disruptions in transportation networks and transforming transforming safety risk and requiring costly repairs. And in addition, this example underlines the importance of maintaining proper clearance distances, continuous monitoring of line conditions, and ensuring that protection systems operate correctly to prevent such cascading impacts on critical infrastructures. All right. In this slide, I want to outline several practical strategies to prevent faults in power transmission and distribution systems. One key approach is tree pruning, which ensures that vegetation does not come into contact with overhead lines. Animal guards are also used to prevent wildlife from causing short circuit or equipment damage. The installation of shield wires helps protect lines from lighting strikes, reducing the likelihood of transient faults. In colder climate, circulating current to de-ice conductors can prevent ice accumulation that may lead to sagging or mechanical failures, as I show you in previous slides. Additionally, washing insulators is important in polluted or dusty environments to maintain proper insulation performance, and operators must also respect voltage and lead limits to avoid overstressing the system. Finally, incident failure monitoring enables early detection of potential issues, allowing maintenance team to act before fault occur. Together, these measures significantly enhance system reliability and reduce the risk of unexpected outages. All right, in this slide, I want to present the main types of faults that can occur in power system, distinguishing between the transient and permanent faults. Transient faults are temporarily in nature and typically disappear once the fault current is interrupted. They are often caused by external factors such as lighting strikes or brief contact with foreign objects. In such cases, the systems can quickly return to normal operation, and techniques like auto recloser are commonly used to restore service automatically after a short interruption. So I think everybody knows about auto recloser breakers. So you're already familiar in power system one. In contrast, permanent faults involve lasting damages to system components such as insulation failure. So these faults do not clear on their own and require physical repair or replacement of the damaged equipment before the system can be safely re-energized. So understanding the difference between these fault types are very crucial for selecting appropriate protection strategies and ensuring both reliability and safety in power system operations. All right. This slide explains another important classification of faults in power system: balanced, symmetrical, and unbalanced asymmetrical faults. So balance faults occur when all three phases are affected equally, maintaining symmetry between them. Although these faults are relatively rare in practice, they are easier to analyze because the system remains symmetrical, allowing you to use a simplified single-phase equivalent model for calculations. On the other hand, unbalanced faults are much more common and occur when one or two phases are affected differently from the others, breaking the symmetry of the system. And we can say some examples include single line to line, and double line to ground faults. Due to this asymmetry, analyzing such faults is more complex and requires specialized methods, mostly the use of asymmetrical component, which decompose the system into balance sets to simplify the calculation of the fault currents. All right. This slide is showing the different type of faults in a three-phase power system, highlighting how abnormal connections between phases or between phase and ground can be occurred. In a balanced system, the three-phase A and B, C operate independently, but faults introduce unintended paths for current flow. This diagram is showing common fault conditions such as single line to ground, we call LG fault, where one phase is connected to ground, line to line, or LL fault, where two phases are shorted together, and double line to ground, or LLG faults, where two phases simultaneously connected to ground. Each configuration results in different fault currents indicated in the diagrams, which affect system stability and protection strategies. Understanding these fault types is essential for designing protective devices like relays and circuit breakers, as each fault produces distinct current patterns and require appropriate detection and isolation to maintain system reliability and safety. All right, this slide is highlighting the relative frequency of different types of faults in power system, emphasizing which ones you are most likely to see in practice. The most common fault is the single line to ground fault, accounting for approximately 70% of the all faults. This high occurrence is mainly due to environmental factors such as lighting, insulation failures, or contact with trees and ground objects, as I discussed before. The next most frequent is the line-to-line faults, making up about 50%, followed by the double line to ground fault at around 10%. And finally, the balance three-phase fault is the least common, occurring in only about 5% of cases, but it is often the most severe in terms of the system impact. This distribution is also very important for power system design, as it can guide us to prioritize protection schemes that are most effective against the most probable faults, particularly single line to ground faults. All right. Uh, in this slide, I want to explain that how the severity of the faults is in power system is can be evaluated, mainly based on the magnitude of the fault current. In general, a fault is considered more severe when it produces a higher current, as this can cause a greater thermal and mechanical stress on equipment. Among all fault types, the balance three-phase fault is typically the most severe, because it involves all three phases equally and result in the maximum possible fault current. However, this slide also emphasized that in certain situations, a single line to ground fault may become more severe than expected, depending on the system grounding and condition and impedance conditions. Other fault types, such as line-to-line or double line-to-ground fault, are generally less severe in comparison, and understanding fault severity is very critical for selecting appropriate protection equipment and ensuring the safe and reliable operation of the system, as I told you. All right. This slide introduced the concept of fault resistance, denoted as RF, and its impact on fault behavior in electrical system. In the case of the bullet or solid fault, the short circuit is assumed to have zero resistance, meaning RF is equal to zero, and which results in the maximum possible fault current. And however, in many real-world scenarios, faults are not ideal and instead exhibit non-zero impedance. For example, an arc fault introduces resistance into the fault path, making RF is not equal to zero, and this added resistance reduces the magnitude of the fault current, which can be beneficial in limiting damage to equipment. On the other hand, it creates challenges for protection systems as lower fault currents are harder to detect reliability. Additionally, since fault resistance can vary and is difficult to predict accurately, it adds uncertainty to system analysis and protection design. So I want to stop up to this slide and have a 10-minute break. Do you have any question? Please, after 10 minutes, please coming to the second link. I will share again. All right. Thank you so much. See you soon, inshallah.